Hello, my name is Jonathan Rivas. Today I'll be solving problem 5.47 on Griffith's Intro to Electrodynamics. So the problem reads, the magnetic field on the axis of a circular current loop, equation 5.41, is far from uniform. It falls off sharply with increasing z. You can produce a more nearly uniform field by using two such loops a distance d apart, figure 5.59. And that figure looks something like this. Alright, so we have this is going to be my z-axis. Yeah. And then here's our circular current loop with radius r. Current goes around like this. Alright. And then we have another current loop down here. Again, radius r. Current goes around like this. And this is going to be a distance d apart. And this will be the midpoint, so z equals 0 here. So part A, find the field B as a function of z and show that dB dz is 0 at the point midway between them. So when z equals 0 here. So he wants us to use equation 5.41. So hi, just really quick, I want to talk a little bit more on equation 5.41. Equation 5.41 can be found on page 227 in Griffith's Intro to Electrodynamics. It's the results from the example 5.6. 5.6 reads that I want you to find a magnetic field a distance z above the center of a circular loop of a radius r, which carries a steady current I. It looks very similar to equation 5.47. The example itself is not so important, but rather the results shows that the magnetic field as a function of z is equal to mu naught I over 2 times r squared over r squared plus z squared, and that to the 3/2. So I want us to use equation 5.41 because the two problems are very similar. They even look very similar. The only difference is that problem 5.47 we have two circular current loops, and example 5.6 is just one. So for our purposes, the only modification we have to make for this equation to change our z, we have to transform our z. Since the two loops are a distance d away, z changes to d half plus z. Right? So the magnetic field is going to be mu naught I over 2 times, I'm going to do it like this, r squared over r squared plus d half plus z squared to the 3/2. Okay, that's one of the modifications. Another modification, or rather something we can employ, is superposition, because we have two circular current loops. We can use superposition to find the magnetic field, the total magnetic field from these two current loops. So we'll just have to add let's see, plus r squared for the second term for the second loop. The only difference is that instead of r squared plus d half plus z, that squared, it's going to be r squared plus d half minus z squared to the 3/2. And this will be for Problem 5.47. We'll have this the magnitude of the magnetic field. It's going to be mu naught I r squared over 2. Now, to account for these two circular current loops, we're gonna need an extra factor. So first factor is going to be 1 over r squared plus, let's see, d half plus z, that will be squared, then that's going to be to the 3/2 power, alright, plus let's see, it's going to be pretty much the same factor, so 1 over r squared plus d half, but minus z squared to the 3/2 power. Alright, that's going to be equation for the magnitude of the magnetic field. Now we just have to take the derivative of this to respect of z. Alright, so that's going to be, let's see, mu naught I r squared over 2. Oops, that was horrible. That's fine. Let's see. I'm going to have a negative 3/2. 2. Let's see. D half plus z for top factor, yes. And that's going to be over r squared plus d half plus z. This factor's squared. All of that to the 5/2. Okay. Plus yeah, same thing, 3/2, negative 3/2, 2 d halves minus z. Then we have another negative 1, and then r squared plus d half minus z squared, all of that to 5 to the power of 5/2. Okay, now we can simplify this a little bit more. Let's see. 3 mu naught I r squared over 2 is going to be negative d half plus z. Yes. R squared plus d half plus z, that squared to the power of 5/2. And then, yeah, then the only thing that changes here is just going to be d half minus z. R squared plus d half plus z, that's squared. And then this to the power of 5/2. Cool. Alrighty. So that's dBdz. But now, here, let me write this down. Sorry. Yes. So this is pretty much first part of part A, right? And now we need to show that dBdz is 0 at the point midway between them, so it's when z equals 0. So we can say dBdz when z is equal to 0, it's going to be 3 mu naught I r squared over 2. So we're going to have, let's see, negative d half over r squared plus d squared 4. That will be 5 to the power 2 plus d half, let's see, r squared plus d squared over 4, 5 halves. Alright, these two are gonna cancel out. You'll just have 0. So 3 mu naught I r squared over 2, 0. And as you can see, we get 0. Works out. And that was part A. Let's see. Part B. Part B reads, if you pick D just right, the second derivative of B will always vanish at the midpoint. This arrangement is known as a Helmholtz coil. It's a convenient way of producing relatively uniform fields in the laboratory. So determine D such that the second derivative of dBdz is equal to 0 at the midpoint, and find the resulting magnetic field at the center. Okay, and it gives you the answer, so we should be expecting our answer to be, let's see, it says A mu naught I over phi square root 5 r. Alright, so that's the goal. Okay, so you're pretty much repeating the steps from part A. You're just taking the second derivative and then evaluating that derivative at z equals 0. Alright, so let's see. Second derivative of dB dz, or rather the second derivative of the magnitude of the magnetic field to respect to z. Sorry, I keep saying the weird stuff. Anywho, alright, let's see. You're going to have 3 mu naught I r squared 2. Let's see how I just have to pay attention to this guy. Okay. We're going to have, let's see. Okay. Negative 1 r squared plus d half plus z squared, that still to the power of 5 halves, plus negative d half plus z, negative 5 halves. We're gonna have 2, and then d half plus z again, r squared plus d half plus z squared, that squared, and that to the power of 7 halves. Alright, plus, let's see, negative 1 over r squared plus d half minus z, that squared, to the 5 halves, plus d halves minus z, negative 5 halves, 2 d halves minus z, negative 1, and all of that over, let's see, r squared plus d halves minus z, that squared, and then that to the 7 half power. Yeah, okay, let me kind of yeah, this will be our second derivative of the magnetic field to respect to z, right? So now we just have to evaluate this when z equals 0. So, right? Yes, at the midpoint. Okay. Let's see. So, okay. We have 3 mu naught I, z equals 0. 3 mu naught I r squared over 2. We are going to have, let's see, we can combine those. Negative 2 over r squared plus d half squared, that to the 5 halves, plus 2 5 halves to d half squared to, okay, all of that over r squared plus d half squared, then that to the 7 halves. This is just going to boil down to, let's see, I can pull 3 mu naught I r squared over r squared plus d half squared, that to the 7 halves. Then I'll have negative r squared minus d squared over 4 plus 5d squared over 4. Okay. And then this boils down to 3 mu naught I r squared, r squared plus d half squared, all that to the 7 halves power, times d squared minus r squared. Now this is only going to be 0 if d is equal to r, right? So in that case, when d is equal to r, we're going to have mu naught I r squared over 2, let's see, yeah, 1 over r squared plus d is equal to r, r over 2, that squared, and then that to the power of 3 halves plus, yeah, r squared plus r half squared, that to the 3 halves, right? 1 over that. And then you boil this down to mu naught I r squared over, let's see, 5r squared over 4 to the 3 halves. And this boils down to 8 mu naught I, let's see, yeah, 5 to the 3 halves r. Yes, and this is pretty much equal to 8 mu naught I 5 rad 5 r. So whichever one, right? So it checks out. Alrighty. And that was problem 5.47. My name is Jonathan Rivas. Thank you so much for watching.